Okay, let's start the session. So, welcome to the seventh tutorial session of Operational Planning of Power Distribution Systems. Whose instructor is Professor Sajid Ganguly sir from IIT Guwahati. So, this is seventh tutorial session. I am Satya, APMRF Research Scholar at Department of Energy Science and Engineering, IIT Bombay. So, in the last tutorial session, we have seen the few of the reliability aspects of the power distribution system, and which have helped you to solve the assignment 6. Now, we will see some of the basic concept how to solve the current and power equation during the power distribution inside of the power distribution networks. So, uh, before uh, so before moving forward, I will give you some of the concept of forward and backward shift load flow algorithm because this was very important. Few of the questions were related to this only. So this numerical method, because there are a lot of methods like Gauss Seidel, you have Newton Raphson method is there. So but forward and backward shift method basically important for the power distribution networks. Okay, so why? Because there's a few reason out of that, like this is mostly applicable to the radial structure, and the second, it is a high r by x ratio is there, because inside of the distribution network large number of load buses are there, one source or slack bus is there. So when you see the typically the network how it is, so suppose this is bus 1, so there will be one generating source from where it is coming. Suppose this is one generating source will be there, and after that you have a one network will be there, and there will be multiple loads which are connected. Suppose this is a one bus where the loads are connected. After that you have another bus where the loads are connected, and this can be connected to some other bus where the loads are connected. Okay, so when you see this network structure, so this is basically a radial structure. There is no ring kind of a structure because for not forming the closed loops, there is a only one direction of flow will be there. Suppose the current is flowing like this, and the second load current is flowing like this, and the third when you see the current is flowing like this. So this is a kind of a radial structure is there. And also when you see the high r by x ratio, why it is there? So have you seen the Yell formula? So you have a conductors inside of the three phase line or the single phase line. So this is the inductance formula. If you remember this, mu naught by 2 pi ln gmd by gmr. Okay, GMR is basically represented 0.7788 times of R, if you know the basic electrical concept. So inside when you see there will be multiple conductors are there inside of the inside the distribution network. So this three phase network is there. So you have a three conductors, and this is the basically the R radius R. So when you closely see the distribution network, their GMD is very very low. GMD is less. Okay, because the conductor spacing is very close. Okay, there is a less spacing between the two conductor, so that's why the GMD is less. So that's why if the GMD is less, so the L actually remains low. Okay, so the X is basically the L omega. So if the L decreases, so X is also decreases. So inside line, when you see this, if x decreases, so r by x ratio basically increases. Okay, in the distribution network. But when you see the overhead transmission lines in the distribution networks, so here there the conductor spacing is more as compared to the distribution network. So that's why there the r by x ratio is low. Okay, so that's why the high R by X ratio is there. So conventional Gauss Seidel and Newton Raphson not much feasible in the distribution network. So and also there is a large number of load buses are there. So there is a less generating. So currently with the increment of the RE sources, so there is a concept of the prosumers basically. So the consumers which can produce the electricity and sell to the distribution network, and flow bidirectionally can flow the current. Okay, and also there is a one also thing is that one source, and in the conventional network, distribution network, you have a one source or a one slack bus. Slack bus is basically it have the infinite inertia which can supply all the power which is required inside of the distribution network. And Also in the radial distribution network, power flows from the source bus to the end sources, which is not in the RE rich cases. But in a conventional system, you have a power flow from the source bus to the end buses, and there is a only one path to flow. So, and this algorithm basically simple, fast, and easy to implement. And we will see the structure that how it is basically implemented. Okay, so you just came through that. In the it is applicable because in the distribution network mostly it is a radial structure, and it have the high R by X ratio, and there is a large number of load buses are there, and there is a only single source or the slack bus is there. So that's why the Gauss Seidel and Newton Raphson is not much suited for the distribution network, and mostly it is suited for the transmission system. But the forward and backward sweep method, this is basically important for the distribution filter to solve the current and voltages. Let's move forward. So basic principle is that the algorithm has the two main steps in this iteration. So when you see the backward sweep or you have the forward sweep. Backward sweep is that when you have the branch current are calculated starting from the last buses and moving towards the source bus. Let me explain that. Suppose you have a source generating source here, and this is connected to the bus here, bus 1, and then you have a Rx is there in the line, then you have one load here, and then again there is a bus is there, and you have a Rx, and then you have a one load again, and then you again have a one bus Rx, and then you have a load. Okay, so when you see here, so this is bus 1, bus 2, bus 3, bus 4. Okay, and here when you see, this is the load 1, load 2, load 3. Okay, let's take one. Suppose the current which is flowing from the source in, from here the current which is flowing, it will move like this, and it will go into this line, then it will move forward, then it move further, then it move here, and then move here. Okay, so at bus 4 when you see current which is flowing, suppose this is I4 current. Okay, so when you see in between the bus 3 and bus 4, what current will be there, that is basically the I4 only. But when you see the in between the bus 2 and bus 3, in between bus 2 and bus 3 and bus 3, so it will be summation of I4 current plus current which is flowing towards the this is 2, this is so this is I3 current. So current flowing there is the I3 plus current going into the load I2. Okay, this is phasor sum. And when you see in between the bus 1 and bus in between the bus 1 and bus 2, so it will be basically I1 phasor plus I2 phasor plus I3 phasor. Okay, so here when you calculating the branch current, this are they are you are considering the last buses, then moving towards the source side, because the current you have calculated, then you are moving backward side, and then came to the source and find it out the what is the voltage is there, whatever the current is there. Okay, in the second, when you see the forward sweep, there is the bus voltages which are updated starting from the source and moving towards the end buses. Okay. So in this you calculate the first the voltages. You already know the voltages. Suppose you find out the voltage here, then you move forward in the end edge direction and then towards the end side. So this is the basic difference between when you move from the backward side and you move from the forward sweep side. Okay. Let's see further what is the algorithm is there basically. Suppose you have a certain bus here. Suppose this is source bus, and you have a here connected through the bus 1, and you have a Rx, and this is connected to bus 2, and you have a load. Okay, so when you see the current is moving from the here, it is moving here, it is moving here. Okay, so this is basically the load. Okay, and this load will consume certain power and certain reactive power, real power and certain reactive power. Okay, so this is basically, suppose I am considering, suppose this is ith bus, so SI will be equal to, which is being consumed inside of this load, is basically SI is equal to PI plus JQI. Okay, so This is basically the whatever the power is being consumed and the reactive power inside of the load, that is we have already know that is which will become out to be SI is equal to PI plus JQI. And then you know the bus voltages. Bus voltages means it will be already given certain buses. Suppose you are starting from V2 is equal to the bus has voltage V2, here it is V1. V2 will be initially when the load is not active, then it is a 1 angle 0, and the V1 is equal to 1 angle 0. But as soon as the load go into the load started consuming the power and the real power and the reactive power, this voltage is going to change. Okay, and one voltage you have to take as a reference, and then second voltage you can find it out. Okay, and there is a one equation that is SI is equal to VI conjugate. We already know VJ, SI and II conjugate. Or you can find out the current from here. II what will be there, SI divided by VI, and you can take the conjugate of conjugate, it will become II. Okay, and then you can find it out the current, because whatever the current going into the other network, other loads, that can be summed up, and what the current it is flowing to the jth network, jth kth, then after that the all the buses will be there, and you can sum and you kill the get the current which is flowing to the this radial network. And the voltage, if you wanted to find, suppose this is a V1 and V2 is there, so V1 will be equal to V2 plus I which is flowing through that network, and R plus Jx. Okay, so all you can say that V2 is equal to V1 minus I which is flowing from 1 to 2, and Zi Ij or Z12. Okay, in between. So this is the way to find out the what are the voltages is there, what are the current is there. Okay, suppose let's take the steps what is will there. First, identify the bus data. Bus data is basically the voltage, impedance, and also volt V comma Z, and also the angle. Okay, that is very important. Or if it is not given, also P and Q will be given sometimes. So through that you can find out what is the power being consumed inside that, and you get the bus data, load data, and the line impedance data. Okay, assume some assumption will be there कि initial iteration will be such that कि VI will be equal to 1 angle 0, and you find out the current, then voltage, and then you can see the in the second iteration it should be less than the certain tolerance band. Suppose it will be given 1 e to the power minus a 0.001 or 0.0001. So this is a kind of tolerance between the second iteration and the first iteration. Okay, and if it is in between the tolerance band, you can move forward that it is a exact solution. If it is not in the tolerance band, you go in the second iteration, third iteration. Okay, so there is a advantages which we have already seen, that it is simple and easy to understand, fast for the radial network, requires less memory because less iteration will be there, and convergence is faster, and good convergence with the high R by X networks in the distribution network basically. And this is mainly suitable for radial network. You have to be some use some other matter for the means circular systems, and also it is modification for needed modification for the mesh, and load modeling is important, and capacitor regulator you have to be model accurately to see that what are the current is going inside that. Okay, let's move forward and see one example. Suppose there is a three bus radial distribution system is there, and there is a one bus that is slack bus which generate the all the power, and it have an infinite inertia which give the all the power which is required inside of the distribution network. And the load buses which is we already know P and Q will be there, and bus 3 is also load bus. So suppose this will be like this, one source will be there, this is the bus 1, and then you have a Rx, and it is connected to bus 2. Bus 2, here the load is there, load, and then you have a R line Rx, then you have a load. Okay, this is the bus 3. Okay, so when you see that, and also this S2 is already given. Okay, S2 is given means it is consuming zero point 0.5 of power. Power is equal to zero point 0.5 pu, and Q is equal to zero point 0.3 pu. And here when you see the power will be equal to zero point 0.4 pu it is given, and Q is given as 0.2 pu. Okay, and Z12 is given. So here the second data is given, that is line data. Line data is 0.01 here, R, and 0.02 J. Okay, and then you have a 0.015 between the line 2 and line 3, and J 0.03. Okay, suppose we wanted to find out the current. Okay, so current equation we already know, I is equal to, from here basically, I is equal to S by V conjugate. I2, if you wanted to find out at the bus 2, so S2 divided by P2, V2, sorry, conjugate. Okay, S2 you already know, S2 at the bus 2, that is already given, that is a zero point 0.5 per J, zero point 0.3, and V2 is we don't know, so there is an assumption that you always consider at the initial point as 1 angle 0 degree. Okay, and then you can find it out that S2, what is it here, zero point 0.5 plus J 0.3 divided by 1 angle 0 degree conjugate, so it will come out to a zero point 0.5 minus J 0.3. Here also when you see zero point 0.5 J point minus zero point 0.3. Similarly, you can also find out what is will the current, that will be S by V of conjugate. So it will come out to be zero point 0.4 minus J point 0.2. Now important point is that what is the current flowing from the second line to the third line. Okay, line 2 to line 3. When you see here, so this is a bus 3, so the current which is flowing here and current which will be flowing here, so current which is flowing from bus 2 to bus 3 will be similar to the load which is connected to the bus 3. Okay, so that's why it is similar to the I3, so that is a zero point 0.4 minus J point 0.2. And what is the current flowing from 1 to 2, from here to here, so it will be sum of both the currents. So here when you see, it is a I2 plus I23. When you sum both, it will come out to a zero point 0.9 minus J point 0.5. And if you wanted to find out what is the voltage here, suppose the voltage, what is the voltage here? So it will be similarly, here is the 1 angle 0 degree plus the current multiplied by Z. Okay, so it will be simply V2 is equal to V1 minus I12, which is the current flowing in that line, and then you can subtract. Similarly, you can find out the for the V2 magnitude you can take. Similarly, you can find out for the V3 also. Okay, I'm not going into the that. We are moving forward that key, how to solve, and if you are getting the clarity out of that. Okay, if you have any problem, just let me know in the chat box, or you can open your mic and ask. Okay. So this we have already we have seen that if you have a buses connected buses at which the load is connected, the current will be go inside of that. So it's a one-way direction. It is not a kind of distribution load which is generating certain power. Okay, this is a one unidirectional flow is there. Let's move forward. Try to solve few of the problems. Okay, that will give you the clarity. First, we will see some theoretical problem. After that, we will see some of the basic numerical problem. Try to solve this. Okay, I got one answer, option B. Okay, that's true because we already know that in the distribution network, forward and backward sweep load flow algorithm basically important for the distribution network. Okay, and distribution network have the high R by X ratio. Okay, and it is also important, that is the radial distribution networks. Okay, and nuclear, no, this is not correct, option B is correct. Okay, so here I have given the some description out of that. When I will upload the slide, you can read it out. Okay, let's move forward, try to solve this. Okay, option B. Okay, okay, that's correct. The option B is correct because we have already seen that key there is two methods, that is backward method and one is the forward method. Okay, Forward method, we start from the source and go towards the end load, or in the backward we start with the end current and then move towards the source. Okay, that's true. That key option B is correct. Let's move forward, try to solve this. Okay, that's true. That option C is correct because in the forward shift we move from the slack bus where the generating units is there, and then there is a RX, and then there is will be load, and then RX, then there will be load. So this kind of a structure will be followed. Okay, and also here very important point, you should see few of the definitions which is very important. Just go through that. What is the slack bus? Basic differentials. What is the PQ bus or load bus? Okay, PV bus. What are the, or it can be called as generator bus. Okay, so go through this kind of what are the different buses will be there. Okay, what are the answer? A, B, C was the answer. Oh, okay. Let's move forward. Try to see this. Okay, option B. Okay. Oh, that's true because we have already seen that it is mostly applicable for the distribution network where the high R by X ratio will be there. And why the others are not correct? Because it requires the formation Jacobian. No, that we have seen in the Gauss Seidel or in the other methods will be there. So not in the forward backward shift. And also only a cable to balance. No, distributions networks are basically unbalanced. Okay, that we have already seen in the first tutorial session. They are mostly unbalanced. Okay, it ignores load current false. We needed load current for that. Okay, let's move forward, try to see this. Okay, so that's true that all bus voltages are assumed to be 1 pu. That's true. Okay, so we usually assume that when the voltages are not given at the buses, we assume that the voltage will be equal to one angle degree, one angle 0 degree. Okay, suppose let's take one example. Suppose the one generating source is there, and there is a one load here. It is connected. Here is the load one, and then you have a RX. Then it is connected to load two. Okay, suppose the current which is flowing here is the I2. Here what is flowing here is the I1, and the current which is flowing here is the I. Okay, so the current which is flowing here is the I2 same, and the I will be equal to I1 plus I2. Okay, when you see here the voltages, when you consider here, suppose here the P and Q is given, so or S is S, you can find it out. So current I2 will be equal to S by the voltage which is there initially here, the conjugate. Okay, so so it will be such that, so by this you will find out the I2 which is flowing here, and similarly I1 you will find it out S by V of conjugate of here. Okay, and then you can add both, you will get the current which is flowing here. Okay, after that you will find out the, suppose the what is the voltage here. Okay, so the current when it flow, the voltage will dip. Okay, when the demand, the power will be required in this. So in the this is important point, when you remember the power is mostly is a coupled with the frequency, and Q is mostly coupled with the voltage. This is the transmission line network, transmission network. Okay, but in the distribution system, distribution network, this is very important that P is also coupled with V. Okay, because there the R by X ratio is high, you cannot neglect the effect of R. Okay, when you remember the equation, power is equal to EV by X sine delta. Okay, here when you see we have neglected R to 0. Okay, because here the X by R ratio is low, R by X ratio is low. Okay, but when you see here the R by X ratio is high, we cannot neglect the R here. So that's why the coupling is also there in between the power and V. This is very very important, you should always remember. So when you see here the uh, power which is going here, the power if increases, the voltage will dip. Okay, the voltage will dip as soon as the power started increasing here. Okay, so it will start the voltage to dip at some value, but it will dip. Okay, let's move forward. So remember there that na कि power is proportional to V in case of high R by X ratio case, which is there in the distribution network. Okay, so this is very very important, remember this. Which option is correct? Okay. Okay, so I got the mostly all the answers as option C. Okay, that's correct. Because we already know that the mod of Vi, suppose the ith bus is there, k plus 1 means if it started from the kth first iteration, so it will second, third. So the previous iteration, that is Vi plus Vi of k, it should be less than the epsilon. Epsilon is basically the tolerance band. Okay, which can be specified that 0.001 or lower than that. So based upon the what the computation power is there, how much iteration you need, how much capacity is there, so based upon that the tolerance band is basically defined. Okay, let's move forward. Okay, so this is going to be a series of problems. Here we will see. So the important point here I wanted to explain that the structure of these problems. So there are 10 problems, questions are there. So each are connected. Okay. So in each I will show that key the network how it is there. So first let's see the statement what is given. Then we will see the what are the questions are there. So there is a simple radial distribution network is there with buses N1, N2, N3, N4 and 5. Okay. N1 is given as the substation of the slack bus and the base MVA is given 1 MVA and the voltage is given 1 angle degree. This is the initial voltages which we considered, and the V N2 and N1 is given 1 angle 0 degree. Means all the voltages which is given, that is a 1 angle 0 degree. Okay, so the at the all the nodes when you see the loads are connected. Okay, so it is something like this. So line connections are there. So it is starting from the one slack bus here, N1. Suppose this is the node 1 where the slack bus is there, and then we move forward, you have a impedance here, and then there is a N2 network is there where the load is connected, and then you have again one network is there, that is N3 where the load is connected. Then again you have a N4 where the N4 is connected, and then again there is a N5 is connected. Okay, N5 node is there. So this is basic structure, the N1 to N2, N2 to N3 and N2 to N4 it is there. So let me erase here. One second. Uh, hmm. Class one. Class. बोलो. हम्म. अच्छा किससे? अच्छा. अच्छा. अच्छा ठीक है मैं बात करता हूँ. ठीक. ओके. Okay, so let's see that. So the structure is very different. So let me erase this. So I have taken some wrong assumption. So this is the source plug bus. So this is the network N1 where N1 to N2 there is a connection. So this is the N2 where the connection is there. And then there is a N2 to N3. Suppose this is I am considering N2 to N3 here. Okay. N2 to N3. So this is the one line. Okay. So and then you have a L3 line. Suppose this is a L1. So this is a L1 line. N2 to N3 there is a L2 line, and there is a one more line which is connected between the N2 to N4. Okay, so this is like this. Okay, so this is N4. Okay, line. Okay, so this is L3 basically. Okay, so and there is a one line in between N4 and N5. So N4 and N5 will be something like this. N5. Okay, so this is called as line L4. Okay, so this is the overall structure of line is there. So the loads are also connected. Suppose this is the load. This is connected at N2, N3, N4, N5. So there is a no load at N1. So there is a load at N2 here, and there is a load at N3, and there is a load at N4, and there is a load at N5. Okay. Okay, so these are the all the loads which are connected. And also the feeder is something N1, N2, N3. So this will be N1, N2, N3, and there will be N2, N4, 5, N2, N4, and N5. And there the all impedances are also given. So if I write it down, this is the Z12 in between, this is a Z23, this is Z24, and this is Z45. Okay, so this is the overall distribution network which is given. Okay, now what is finding out, you have to find it out, what is the load current phasor at a N3 at a first iteration. Try to solve this. It is easy to solve, just I wanted to see the what is the structure you are going to follow. Okay, I have already given the instruction how to solve that. Try to fit in this question and try to solve this. If you face any problem in making this network or trying to difficulty in solving this question, just let me know. Okay. If you don't have calculator, just take it from somewhere. Okay, that is very important. Okay, option B, I got one answer. Let's wait for 10-15 more seconds. After that, I will give the solution. Okay, let's see what is the correct answer is there. So, so in the exam, this formula will be provided. No, you already know this equation. No, I don't think it will be given. Okay, I think professor is also taking this tutorial session of this, so you can ask directly to prof. That is very difficult to give these answers by me. Okay, so let's try to solve that. This is basic equation you already know. S is equal to Vi conjugate. Okay, so when you take the conjugate of suppose S conjugate, V conjugate, I conjugate of conjugate, it will be similarly equal to conjugate. So you can say that I is equal to S by V of conjugate. Okay, that is simple problem. Simple method to understand this. Okay, let's try to solve this. So the I3 is equal to I3, that is already given. S is equal to VA conjugate. So when the I3 wanted to find out S3 by V3 conjugate, what is the S3 given? S3 is given here. Okay, it is a 0.25 plus j 0.15. Okay, and the V is already given. V3, the initial voltage angle 1 angle 0 degree. Okay, so when you take the conjugate of that, so it will be 0.25 minus j 0.15. Okay, so it will be simply equal to I3. Okay, so it will be 0.25 minus j 0.15. Okay, so I think nobody have given option B. It is given, so option B 0.25 minus j 0.15, that is correct. Option B is correct. Okay, let's move forward. Try to find out the current phasor at node 5 in the first iteration. Try to solve this. Let me take from here this structure. One second, wait for 1 minute. Just okay, try to solve this. Okay, option B. That's easy, no? Okay, you already know how to solve option B. That is correct. Okay, so you already know what is the methodology to solve that. You already understood that okay, what is the voltage will be given and what how to find out. So we already know how to find out. That is the current at a node 5 will be equal to S by S at a S5 divided by V5 conjugate. S5 is already given. What is the load which will go? That is 0.35 plus j 0.22 divided by 1 angle 0 degree of conjugate. So it will be 0.35 minus j 0.22. Okay, so that is correct. Let's move forward. Where determine the line current which is going current in the line L4 and 4 to N5. Let me copy this. That is very important to solve the problems. Okay, just paste it here. Option is not coming. Okay, then it's fine. Okay, I got one answer, option C. Okay, anyone else? It's easy. Just observe the problem and you will get that. Okay. Just observe that. What is given and what is asking. What you already know. I'm giving you few seconds to solve. Just observe that. Okay. If you are facing any problem, just let me know. Okay. So that I can clear that doubt. Okay, let me give the solution. So when you see here, so what is asking? What is determine the line current in the line L4? Where is the line? This is the line L4. Okay, this. Okay, so it is asking what is the current which will go from N4 to N5. So when you see here, the only one load is connected. So current which is flowing inside of that load will be the same current which is flowing from the N4 to N5. Okay, so it is like this. So this is like this, it is connected. So here the load is there. So this is the N4. Okay, so this is N5. Okay, and this is Z45 and the load connected here. Okay, so when you see the current which is flowing here, that will be similar to the current which is flowing here. Okay, so what was the current which was flowing? It was 0.35 minus j 0.22. Okay, so that will be similar to option A. Okay, 0.35 minus j 0.22. 0.35 minus j 0.22. So option A is actually correct. Okay, not conjugate of that. Okay, try to solve this. Let me paste it. Okay, option B, I got one answer. Okay, let's wait for a few more minutes. Just other to also to understand the problem. So it is already given. Na? So I will explain that. So try first, try it by yourself. Okay, option B. Okay, just wait for a few more seconds. Okay, let me give the solution. Okay, so when you see the overall network, the N2 to N4, it is asking what will be the current which is flowing. Okay, so when you see the N2 to N2 network, N2 to N4 network, so N2 is connected like this. N2 is here. So there is a one load which is connected at N2, and there is a one line which is the Z24, which is connected at node 4, which is the N4, and then you have again a one line, and then which is connected to N5, and this is the load. Okay, and here also you have a one load, though this is the Z45. Okay, so in the question, it is asking what is the current which is flowing at L3. L3 is basically this. This is the L3 line. Okay. So what will be the current flowing here? Okay. So when you observe that the through KCL only, so the current which is flowing in this load and the current which is flowing here, so at this, if you consider this is a one bus, so the current which is flowing from through the L3 is basically the current growing here. Suppose this is the I1 and this is the I2, the current going into the I1 and the current going into I4 and I5. So current will be simply equal to I4 phasor sum plus I5 phasor sum. Okay. So the I4, what will be the value of I4 which is flowing here? So it is basically the S4. S4 is given zero point 0.4 plus J zero point 0.2 divided by 1 angle 0 degree of conjugate plus I5. I5 we have already find it out in the previous problem, that is 0.35 minus point J22. 0.35 minus J0.22. Okay. So when you sum it both, this will also come out to be zero point 0.4 minus J0.2 plus 0.35 minus J0.22. Okay, add it up, it will come out with 0.75 minus J0.42. Okay, it will coming out to be option B. Okay, you just have to apply the KCL. Okay, you no need to be understanding of the moving from the forward side, you just move from the backward side, so it will be easy to solve. Okay, just find out the current which is flowing here, I5, then find out I4, just sum it up, I4 and I5, that is a phasor sum, and you will get the answer, 0.75 minus J0.42. Okay, here it is given solution. Let's move forward, try to solve this. You have to find out what is the line current L2, N2 to N3. Okay, option A. I got one answer at option A. Let's wait for others. Option A. Okay, two option A's. Let's wait for others also to solve. Okay, just for few more seconds. Okay. So the current which is flowing into the N3, that is load at node 3, that is correct, option. So when you see the S5 is already given, sorry, N3, the load here it is connected N3 is 0.25 plus J 0.15. So current when you find it out, it will be equal to 0.25 plus J 0.15 divided by 1 angle 0 degree of conjugate. So when you find it out, it will be 0.25 minus J 0.15. Okay, that's correct. Option E is correct. Okay, let's move forward. Try to solve this. Try to solve this. Okay, I got option B. Let's wait for others also to solve. Okay. Okay, option A. Let's wait for a few more seconds. Option B, I got two, three answers. Okay. Okay, option A. Okay. Just wait for a few more seconds and re-verify whether it is correct or not. Okay, let me give the solution. So when you see from the node 5, node 2, that is a node 2, and there is a one node 1 is there. So it is asking what is the current will flow in between this. Okay, when you see this, the N2 to N3 network, so we have already found it what is the current will be flow. Okay, and also in between N2 to N4, we already find out what is the current will flow. Okay, let's see from at N3 what was the current, that is 0.25 minus J 0.15. Okay, that is 0.25 minus J 0.15. And let's see what is the current which was flowing to the N2 to N4. So N2 to N4 it was 0.75 minus J 0.42. Okay, 0.75 minus J 0.45. Okay, 0.75 minus J 0.42. Okay, so this was the overall. Okay, let's see what will be the current which flow from here. So simple case here, you will add it both. So how what it will come out to be, 10 7 to 9 1 1.00 minus J 0.57. Okay, it is not matching. Oh, so what was the current which flow? That is the 0.25 minus a 0.15, and here from N2 L3, N2 to N4. Okay. So here what I have not added here the current which is flowing here in this load. Okay. So the current which will flow that the load which is connected here, that is 0.3 minus j 0.18. Okay. When you sum it, it will come out to be 1.30 minus j 15 and then 7.75. Okay. So option A is correct. Okay. That's correct. So it is easy to make the network and get the current which is flowing here. So I have not considered what was the load connected. The current will flow here also. No. Okay. So this current, and this current summation will be simply equal to I. Okay. Which is flowing from N1 to N2. Okay. Let's move forward. So what 1.30 minus j 0.75. Okay. Let's move forward. Try to solve this. Now it's time to find out the voltages. Use this concept, no? So the voltage as the slack bus is one angle 0 degree. So you need a one reference. Okay. So it supply all the, suppose this is source, no, and this is connected to load node one. So this slack bus supply all the power, real power and reactive power which is required by the load. Okay. So that's why this voltage is maintained at one angle 0 degree, because Q is proportional to V, and the power in the strong distribution line where the high R by X ratio is there, power is proportional to also V. So it supply all the power, all the reactive power. So it voltage is maintained at one angle 0 degree. Okay. Considering that, try to solve this. Okay, let me give the solution for this. So I have already noted down here. So when you see the voltage as the node 1, it is simply given as the 1 angle 0 degree. And so the current, and also we have computed the current which will flow. So let me paste it here. So when you see the current, we have already funded the current which will flow from N1 to N2. Okay, that is similarly equal to IL1. Okay, and the Z12 we already know. Z12 is already given in the network, that is 0.01 and J 0.2. Z12 is given 0.01 and J 0.02. Okay, so what is the value of current? Suppose this is the something like this network is there. So this is N1 and this is N2, and here source is there. Okay, so simple equation, the voltage here V2 is equal to, and this is the V1. Okay, so the V1 is equal to V2 plus I angle Z, Z12. Okay, or you can say that V2 is equal to V1 minus IZ, kind of. Okay, this is simple equation to be known. Okay, but here the problem is that ki, IZ, we will find it out. So multiply, first find out the IZ equation. Okay, IZ, multiply both IZ, you will get this. Okay, just you have to multiply, that is the this equations I have given. So when you multiply both taking the calculator or anything, it will come out with 0.0028 J 0.0185. And then what the simple, we already know this is the 1 angle 0 degree, and IZ we have found it out 0.028 plus J 0.185, subtract it, you will get 0.972 minus J 0.0185. So it will come out to be option first. Okay, so so when you are finding out the current, just move from the load side. If you wanted to find out the voltage, see from the source side. Okay, so if follow the forward side. So that is very important. Okay, just remember the what is the here you have to find use the KVL basically to find out the basic voltages which is there at the particular nodes. Okay, let's move forward, try to solve this. Just remember the currents and voltages which we have found it out. Okay, just remember this. This is the point V2, voltage at V2. Sorry, the voltage V2 is equal to 0.972 minus 0.0185. Okay, V2 we already know, V1 already we know, that is the 1 angle 0 degree because it's a slack bus. Anyone? Take your time. Take your time. No issue. Okay, option A I got. Just wait for a few more minutes. After that, I will give you the solution. Okay, option A to option. Just wait. Let's wait for a few more minutes and re-verify whether it is correct or not. Okay, let me give the solution. So it is asking what is, see, listen here. So it is asking what is the voltage at the node 3. Okay, we already see that key voltage as the node 2, we already know that is already given V2 here, and the current we already know what will be flowing here. Okay, that we have found it out. This is in node 3, so this is the V4, V3. Okay, so V3 will be simply equal to V2 is equal to V3 plus I times of which is flowing in this line and Z23, and V3 when you wanted to find out, that is V2 which is already given minus I which was already we know what was that, that is S3 by S3 is there, so it was 0.25 minus J 0.15 multiplied by Z23. Z23 is given here 0.015 plus J 0.03. Okay, you just have to multiply it and subtract by V2, you will get the V3. Let's see here. That is simply here the current which is flowing to the R2 voltage we have already we know that is a V3, we have already find it out, and then V3 is equal to V2 minus this. Okay, you just have to multiply this and you have to separate, it will come out a 0.96375 so that is option 2475 I think. So it is option nearly option A is correct. Okay, re-verify whether it is correct or not. So this is very simple. So when you find it out the voltage as the previous node, you can find out the voltage at the other nodes. Okay, that is easy to solve. Let's move forward. Try to solve the other problems. Try to solve this. So let me give what is the voltage at V2, that is important. What is the voltage at V2? V2 was basically 0.972 minus minus j 0.0185. 0.0185. That will be easy for you to solve. Okay, option A, we got. Let's wait for a few more minutes. Let's other also to solve. Make sure that you carry the calculator from the next round, so it will be easy to calculate. Okay. Okay. Just wait for a few more seconds. 10, 20 seconds. Okay, let me give the solution. So what we have seen here that this is the node 2 which was there, and this is the node 4. So the line which was connected in between, that is Z24. Okay, impedance is there. So it is asking basically the voltage which is here is the V2, this is voltage V4. So through the equation we already know V4 will be equal to V2 minus current which is flowing into this line multiplied by Z24. Okay, so V2 already we know from here, that is V2 minus the current which will flow inside of this line, which is flowing through this load and this load, N4 and 5. N4 was there, so current here that will be zero point 0.4 minus j zero point 0.2, what was flowing into the I see this fifth load, that is 0.35 minus j 0.22. It will come out to be 0.75 minus j 0.42 multiplied by Z24. Z24 is already given here, 0.012 plus j 0.025. Okay, so and v2 we already know, so from this we can calculate that. So here also I have given here the v2 minus il3 which is flowing there. It will come out to 0.9525, 0.9525, 0.03221. That is option A is correct. Okay, let's move forward, try to solve this problem, that is the voltage at N5. That is last problem of this session. Let me give you what the N4 was there. Voltage at N4, that was V4. V4 was equal to 0.9525 minus J 0.03221. Okay, option A. Through the option you can judge, because 3 is already matching with the node 3 voltage, node 2 and node 4 voltages. So that remaining was the one which is the answer. Okay, option A. Just wait for a few more seconds. After that, I will give the solution. Okay, let me give the solution here. So this is simple problem now. We already know the node 4 voltage, and it is connected to here node 5. Node 5 is having one load. Okay, so the current which is flowing here in the node 5, in this load, it is basically 0.35 minus j 0.22. Okay, so similar current will flow through here as well. Okay, and the impedance which is given here is the 0.01 plus j 0.02. Okay, this Z45. Okay, so when we already know the V4, we have to find out the V5. Okay, so V5 is basically equal to V4 minus I, which is flowing from 4 to 5, multiplied by Z in between 4 to 5. So V5 is equal to V4, we already know, minus the current which is flowing. Current will flow 0.35 minus j 0.22, and Z45 is basically 0.01, j 0.02. When you multiply and subtract with the V4, it will come out to be 0.9446, which was option 9446, option A 0.037. Okay, so these were the problem. These are the easy problems to be solved. One question which is given in the assignment is little bit lengthy, but the methodology to be followed is the same. Just find out the current from the load side and then find out the voltage from the source side. It will be easy to solve. Okay, so what we have seen so far, that is simply what is the forward and backward sweep load flow algorithm, where it was applicable, that is high R by X ratio, radial structure, large number of load buses, because in the distribution network it is there, and there will be one source and the slack bus. And this also we have seen that why this R by X ratio is high. Okay, because the conductor spacing in between is very less as compared to the overhead transmission lines. Okay, that's why the L which was seen mu by 2 pi ln GMD by GMR, GMD by GMR. So the GMD will become lower. Okay, that's why L decreases. L decreases means X is equal to L omega decreases. So R by X ratio will become high. Okay, in the distribution network. So that's why we use the forward and backward sweep method, not the conventional Gauss Seidel or Newton-Raphson method. Also, you should remember that this is applicable to a radial structure. Okay, and it is not applicable. It is also applicable, but not that much applicability there. Where the prosumers are there. Prosumers means ki the consumers which can supply the power. Suppose the solar plant is connected there at the distribution network, and it can supply the through that solar generation, rooftop solar generation, to the grid or discom. So that's why they are not here in the consideration is not there. These are the prosumers. Okay, then we have seen how the algorithm is there, what is the tolerance band it is there, and where to stop, advantages, few limitation, and we have seen one question, and then we have seen few of the problems related to the basic problem based on the definition, and one lengthy problem on the numerical side. Okay, so that's all for the today's tutorial session. If you face any problem, we will discuss in the next tutorial session. If you have any doubt now, just you can type in the chat box. I will wait for 1 more minute. After that, I will end the session. If you have any problem, just let me know. Okay, you can ask. You can ask. You can type also. You can open your mic and ask. That is also fine. Is it applicable to the mesh network? See, it is where I have seen written here the definition when you see it needed some modification for the mesh network. Okay, so it is applicable, but with certain modification will be there in the mesh network. Not directly you can use this method. Okay, any other question? Dig it down that key why it is there, what modifications are required, so you can find it out. But for the solving these problems which is given in the assignment, I don't think it is required because they do not give the mesh network. That is only radial network will be given. Okay. Okay, then that's all for today's tutorial session. We will meet on the next tutorial session on the next Monday. Okay, thank you so much for joining.